Hey everyone, Mr. Chapter back at you with another U-Substitution video. This time we're going to take a look at the technique of U-Substitution itself. So when do you need to use U-Substitution? Well, if you look at a problem, and if you try to take the derivative of it, it would require the chain rule. And I'm asking you now to take the antiderivative of that, or indefinite integration, using some function like that, then you would need to use U-Substitution. It's essentially like the backwards version of the chain rule. So on the left I have the steps to U-Substitution, and on the right I have the problem that we tried to solve in the previous video but were unsuccessful. Let's go ahead and I'll solve this side by side as reading the steps. So obviously the first thing you want to do is check to see if you can do some algebra. Maybe you can put things in terms of sines and cosines, or use some kind of an identity or factor, and that would simplify the problem enough that you wouldn't need to use U-Substitution. You should always check to see if you could do that first. If you can't, step number 1 of U-Substitution is to rename the inside of the more complicated part U. So recall we're thinking about layers here, right? And the chain rule involves layers. So you want to find your function that has the most layers. So in this case it's just the square root of 2x plus 1. And you want to let U equal the innermost layer, in our case 2x plus 1. Step 2, take the derivative of U with respect to x. So your job essentially is to take the derivative of both sides. We're going to start with the derivative of U. Well, we know the derivative of U is just 1, right? So it would be 1 du. The 1 is not necessary. And then you got to take the derivative of 2x plus 1. And the derivative of 2x plus 1 is just 2 dx. Okay? So we're taking the derivative of both sides. Step 3, isolate dx. So you want to get dx alone. In order to do that, you just divide by 2, both sides. And you get that dx is equal to 1/2 du. Okay? Here's the important part. Step 4, substitute the expressions for u and dx into the original integral. So we are now going to take our two pieces we just got. So this 2x plus 1 is now equal to u, and 1/2 du is now equal to dx. And we're going to substitute those into our integral. So our integral is now going to become the integral of square root u times the dx is now 1/2 du. Okay? Step 5, pull any constants out. So in this case, we do have a constant here. We have this 1/2 that could always be, constants can always be pulled out of integrals. So this is 1/2 times the integral of the square root of u du. Step 6, anti-differentiate. Notice the problem at hand now does not require the chain rule, right? I can take the antiderivative of the square root of u by just using my normal integration technique. So let's go ahead and try that. Scooch this down a little bit. So this is now going to equal 1/2 times, now u to the 1/2 power, if I took the antiderivative, I'd have to add 1 to the 1/2 power, right? So I'd have u to the 3/2 power divided by 3/2. And then we're going to do the plus c business, the plus c, okay? So this is my antiderivative. And now I'm going to just put the 3/2, I'll pull the 3/2 up and call it 2/3 again. So this is 1/2 times 2/3 times u to the 3/2 plus c. And the 2's cancel, giving me 1/3 times u to the 3/2 plus c. Okay? So the problem is almost done. Step 7, the last step, is to put whatever u was originally back into the problem. So this u is now just going to be replaced with the original term 2x plus 1, right? Because that's what, I'll just kind of circle it right here, that's what u was equal to. So the final answer is 1/3 times the square root of 2x plus 1. Now 2x plus 1 is, you know what, I'm not even going to use the square root, but it would just be, the power would be the 3rd power, and it'd be a cube root. I kind of like using rational exponents a bit better though, so I'm just going to call it 2x plus 1 to the 3/2 power, and plus c here, okay? And we can leave it all in the parentheses there, and this is our antiderivative.